Okay. Some technical difficulties there, I think. This section will work through deriving the buckling equations that we used way back at the beginning of the semester with the lab working on the buckling equation with the wooden dowels. So when you place an axial compressive load on a structure, like a little wooden dowel using the instron, very often the way that this very slender structure will fail is not yielding or fracture, but this phenomenon that's a bowing or a bending that we call buckling. We worked with the fact that there is a particular load that depends on the geometry, the way the ends are pinned, the length, and the radius of gyration. So the load that this happens is a characteristic load that depends on particular factors, and it's called the critical load or the buckling load. Before we had done beam bending, we didn't really have enough analytic understanding of what happens in structures like this to really go through a rigorous layout of where that buckling stress comes from, but now we do. If we consider a column that is pinned at both ends, we apply our axial compressive stress, and we end up with, if we essentially assign our coordinate system like this, with x along the beam from the base and y being to the left, we have a coordinate system like we've used for the beams in bending so far, where the deflection to the right has been our convention for bending under a positive moment. So the sign convention is that the positive deflection V in the plus Y direction corresponds to a positive bending moment or tension on the bottom surface of the beam. So if we take sort of a zoomed in view of this bottom connection of our beam in bending, we have something that could be sort of considered to look like this. We have our connection point, and we have our coordinate system with x up and y positive to the left. We are then going to have reactions. We have to have a positive support reaction equal and opposite to the applied load. We know that we have that same internal compressive force P, and because this is offset, we know we have to have some internal bending moment. And we know that if we look at that distance, we call that a negative deflection V. So we can come over here and do a statics problem. If we have our reference point O at the section cut at the free surface of the beam, we can say that the sum of the moments at our reference point O is equal to the positive internal M and that applied P, I'm sorry, the applied P has no separation distance, has no line of action, but our reaction force, P, does, and that would tend to cause a negative rotation. That separation distance is a minus V times P, and we know that that has to sum to 0, or the M plus the deflection times the reaction equals 0. But we also know that the bending moment is equal to the bending stiffness times the second derivative of the deflection. So we can say that the bending stiffness times the second derivative of deflection plus the reaction times the deflection equals 0. If we divide through by our bending stiffness, we have V double prime plus the load over the bending stiffness times the deflection equals 0. And if we cast plus, if we define a new quantity, alpha squared, as the load over the bending stiffness, we then have a very tidy looking second order differential equation where we have the second derivative of the deflection plus our new term alpha squared times the deflection equals 0. A very standard second order homogeneous differential equation, the solution to which is always just sines and cosines. So we know that the solution is some constant times our factor, whoops, nope, that is some factor is some constant of integration sine alpha x and a second constant of integration times cosine alpha x. That's always the solution to this homogeneous case. And we can confirm that by taking the derivative and substituting all of this back in. So if we take one derivative, we have v prime of x equals alpha c1 cosine, derivative of sine is cosine, alpha x, the derivative of cosine is minus sine, so we have a minus alpha c2 sine of alpha x. Take another derivative, v double prime, we get another alpha term, and we have a minus, so minus alpha squared, c1, back to sine, and we have derivative of sine is cosine, so minus alpha squared c2 cosine of alpha x. But we know that v double prime is equal to minus alpha squared times the deflection. That's just from the original differential equation. So if we put what we've just had in red on the left side, so minus alpha squared c1 sine alpha x minus alpha squared c2 cosine alpha x, and then we'll change color, we'll make this blue. On the right hand side we're going to multiply minus alpha squared times the original deflection equation, C1 sine alpha x plus C2 cosine alpha x, and distributing that in to both terms, we see that yes, in fact, this is a valid solution. So where does this get us? This gets us to the fact that we have unknown constants of integration. Constants of integration come from the boundary conditions. So what do we know about the physical situation? We know that at the left support, the deflection has to be 0. So if we substitute that in for our original equation, and I wonder if I can copy that's probably getting a little too fancy. So if we copy our equation again, just to have it handy and visible, C1 sine alpha x plus C2 cosine alpha x. Alright, so now back to our boundary conditions. We know that at the left support, we know the deflection is 0. So 0 equals C1 times sine of 0 plus C2 times the cosine of 0. Well, this guy is 0, this guy is 1, which gives us 0 plus C2 plus 0 equals 0. C2 has to equal 0. So that gives us that the deflection equals C1 sine of alpha x. What else do we know? We know the other boundary condition is that at x equals L. We know that v of x has to equal 0. So therefore 0 equals C1 sine of alpha times L this time. So this C1 sine alpha L term, there are a number of ways to make this equal 0. There are several conditions that will make this term 0. And the things, or some of the things, and let's make a little bit more room. So some of the ways, or the 3 ways to make this 0, C1 sine of alpha L can be 0 if C1 itself equals 0. What does C1 equals 0 imply? This implies that there is no displacement. Okay. Another way that this is 0, if we remember how we defined our alpha, so a side note over here, that alpha squared is P over EI. So another way that this C1 sine alpha L term could be 0 is that alpha is 0. How is alpha 0? that would imply no load, which is not necessarily a very interesting case, but it is a possibility. And then the third way that this could be 0 is because this is a sinusoid, if the argument of the sine, if the alpha times L term is equal to pi, 2 pi, n pi, where n is an integer, that also equals a 0. So, in summary, the lowest non-zero load which satisfies these conditions, or that satisfies a 0 condition, is when the alpha L, the argument, equals pi. Alright, so if our alpha L equals pi, then alpha squared L squared equals pi squared, and we know that alpha squared equals pi over EI. Well, if we take this definition of alpha squared and solve this for alpha squared, we see that alpha squared equals pi squared over L squared. So we then take these two terms we have the P over EI version of alpha squared. So alpha squared equals alpha squared. We have P over EI equals pi squared over L squared. And if we solve this for P, we have pi squared times the bending stiffness over the length squared, which is a familiar quantity from earlier in the semester in the buckling lab. Now, when we did this before, we threw an extra term in the denominator over K L squared, where K is a factor that accounts for the fact that maybe the ends are not a true pinned condition. So if I scroll on down, we've got a little bit of text regarding to this. This is the critical load, also called the Euler load, and to consider different conditions, different end binding conditions, such as fixed, fixed free, or fixed pinned, you have to make two changes. One of those is using the effective length of the free column, and the other is the modifier factor K for end effects. But that little bit of calculus is where the critical buckling load comes from.